Hey everyone, welcome back to another video. Today's topic, inductive reasoning. Let's get started. To start off today, we're going to look at this pattern and we're going to see if we can find the next three numbers to this pattern. The pattern begins at 101, then it gets to 89, 77, 65, and our goal is to find what are the next three numbers that would follow after this. So, by looking at this pattern, I can see that the numbers are actually getting smaller. Normally, when numbers get smaller, we can be either subtracting, we can be dividing, or we can be multiplying by a fraction that's smaller than 1. So let's go ahead and look here to see which of those three. I usually like to test out subtraction first because if it's subtraction, that usually tends to be the easiest one to work out, so I always hope it is subtraction. So let's go ahead and see if we can find a pattern that fits with subtracting. To go from 101 to 89, if I'm subtracting, they would have to subtract 12 each time. Then going from 89 to 77, we want to see, well, does subtracting 12 from each number work? And we can see that 89 minus 12, in fact, is 77. 77 minus 12 would be 65. Therefore, I can tell right now, based on this work, that the pattern definitely is subtracting 12. So in order to find the next three numbers, I just continue to subtract 12. 65 minus 12 would simply be 53. 53 minus 12 would get me 41, and 41 minus 12 would be 29. So therefore the next three values to this pattern would be 53, 41, and 29. What we just used right now is what we call inductive reasoning. The formal definition to inductive reasoning is a type of reasoning that reaches conclusions based on a pattern or specific examples or past events. So we found the next three numbers based off what happened in the pattern before. Whenever you find a solution to a problem based on a pattern or based on past events that are happening, you are using inductive reasoning in math. So let's go ahead and continue to use inductive reasoning to solve this next one. Again, we're looking for the next three numbers. So here we have 9, 6, 4, and 8/3. So again, I see a trend of numbers going from bigger values to smaller values. So right off the bat, I can tell that it's either going to be subtraction, division, or multiplying by some fraction that's smaller than 1. Then I can't help but notice the 8/3. When I see a fraction, and knowing that the number before it was a whole number, that usually tends to lead me to believe that now I'm either dealing with division or multiplying by a fraction. Now for this one, in this specific example, I can tell that it's probably going to be multiplying by some fraction. And what we can do to find that fraction is we can divide the second number by the first number to let me know what they're multiplying by. So if I take 6 and divide it by 9, that leads me to a simplified fraction of 2/3. So now I'm going to check to see, well, does multiplying 2/3 end up giving me this pattern? Let's find out. 9 times 2/3 is 6, which is the second number. So then if I do 6 times 2/3, I should be getting 4, which 6 times 2 is 12 over 3, which ends up being 4. So I did get the next number. And again, multiplying 4 by 2/3 results in 8/3. So now I know they're multiplying by 2/3. So in order to find the next three numbers, I simply have to continue to multiply by 2/3 to find those numbers. So their pattern was multiply by 2/3. They multiply by 2/3. And again, this is how we use, right now what we're using is inductive reasoning. We're using this reasoning of the pattern to help us find the next numbers. So then 8/3 times 2/3. We're going to go ahead and continue it right here where we left off, on the bottom. 8/3 times 2/3. 8/3 times 2/3. 8 times 2 is 16. 3 times 3 is 9. That would be our first value. So 16 over 9 would be the next number that comes up in that pattern. Multiplying by 2/3 again, we would get 32 over 27. So the next number in the pattern would be 32 over 27. Let's multiply by 2/3 one more time to find that last number. Times 2/3, we would get 64 over 81. Leaving our last number to be 64 over 81. So these three would be the next numbers that pop up in our pattern. And we'll leave them like that. Okay. Now this is one way to use inductive reasoning again. Now inductive reasoning doesn't have to involve numbers. Sometimes there's patterns that don't involve numbers. So let's use inductive reasoning to find a pattern for this sequence. So let's go ahead and let's start solving this problem. It says find the pattern of the sequence, use the pattern to show the next two terms. And here we have the abbreviations to the states of the United States. And we can see that they're going in alphabetical order. So we would need to choose the next two states that would come up in alphabetical order. These are not in alphabetical order, so that would not be the answer. Although these are in alphabetical order, they are not the correct ones that would follow California. So that is also not the correct answer. Again, these are also in alphabetical order, but these are not including the ones we need. So it's missing one. Here we finally have the two states that would come after California if we were listing them based on their abbreviations in alphabetical order. So this would be our final answer. And this is how you use inductive reasoning to help you solve some problems. Now, another thing that is usually created when you use inductive reasoning is what we call a conjecture. A conjecture is an unproven statement or rule that is based on inductive reasoning. So a lot of times people will create rules which they call conjectures based off inductive reasoning. But a lot of times we can't really prove them. But what we can do is I can take someone's conjecture and try to find what we call counterexample. A counterexample is what we use to prove conjectures to be false. Okay, a counterexample is an example that shows a statement or conjecture is false. So although conjectures are usually unproven statements, they can be proved wrong. And that's what we use counterexamples for. So now we're going to look at some examples of some conjectures and try to see if we can find a counterexample that'll prove that conjecture to be false. So here we have this problem. It says, consider the conjecture. Any number divisible by 2 is also divisible by 4. So they're saying if we take any number and we can divide it by 2, that number will also be able to be divided by 4. And here we have a list of numbers and they want us to check. Are these counterexamples? Yes or no? So let's go ahead and let's start checking them. We see 12. Is 12 divisible by 2? Yes, because 2 times 6 is 12. Now is 12 divisible by 4? So 12 divided by 4 is 3. So it is in fact divisible. So therefore I cannot use this as a counterexample because it actually proves the statement to be true. So I would mark this no. This is not a counterexample. Let's look at the number 19. 19, is it divisible by 2? It is not. Is it divisible by 4? It is also not. So this one doesn't really tell me anything. I cannot use this one because it's not divisible by 2 in the beginning. I need the number to be divisible by 2 and then to prove that it's not divisible by 4. So this is actually also not a counterexample. Although it got 2, like it's not divisible by 2 doesn't mean that it is a counterexample. 22. So 22 is divisible by 2. 22 divided by 2 is 11. 22 divided by 4, you would get a fraction or a decimal. So because 22 is divisible by 2 and not divisible by 4, this proves that conjecture wrong. So I can actually use this one as a counterexample. 28. Now let's look at 28. Is 28 divisible by 2? Yes. 28 divided by 2 is 14. Now is 28 divisible by 4? Also. So again, this number is simply proving that statement true, so I cannot use this one as a counterexample. The last number is 30. 30, is it divisible by 2? Yes. 30 divided by 2 is 15. And 30 divided by 4, again, that would give us a fraction or a decimal. So because that's not a whole number, I'm not allowed to divide it by 4. It's not divisible by 4, which means 30 would actually also be a counterexample because it's a number that can be divided by 2, but not by 4. So we can now prove that, hey, this statement is false. We know that statement is false. Here are 2 numbers that prove that statement is false. This is how we prove conjectures wrong. So let's look at another example of how we try to find a counterexample to prove a conjecture wrong. Here it says, find one counterexample to show the following conjecture is false. And here's what the conjecture says. ABC is a right triangle, so angle A measures 90 degrees. For those of you that don't know what a right triangle is a triangle that has one 90-degree angle. So the conjecture is saying that if ABC, triangle ABC, so if the triangle has sides A, B, C, it's saying that angle A will always measure 90 degrees. So we need to find an example that proves that wrong. So let's go ahead and look at these 4 that they've given us. I have 2 options out of my 4 that are not even right triangles. So I cannot use these to prove that conjecture wrong. Option C shows me a right triangle where angle A is in fact 90 degrees. So this is an example of one that would prove that conjecture to be correct. Can't use that one as a counterexample. B is also a right triangle, has corners ABC, but notice here the right angle is on angle B. Therefore, because angle A is not 90 degrees in this sample or in this example, I can say that B would be the correct answer. This would prove that conjecture wrong. So I hope this lesson, this mini lesson sort of on inductive reasoning, has helped you get a little bit of an understanding on what it is, how we use it, and also that you now better understand what a conjecture is and how to prove conjectures wrong with a counterexample. As always, if you have questions, feel free to leave them in the comments and stay tuned for other videos. Thanks for watching. I hope you like and subscribe.